Great. So, well, welcome again to the Cardamom seminar series. So we're very happy today to have Nils Reimers talking from Hugging Face. As Nils has a lot of expertise in natural language processing, particularly some models like SentenceBERT, the SBERT model that we've all probably used in our research and is a great model. He obviously did his PhD in Darmstadt, and since then been working on all kinds of things. And today he's going to talk a little bit about how some of these techniques, particularly these very deep learning techniques, can be applied to some of the less resource languages, like we have in the Cardamom project. So Nils, if you're ready, if you want to just share your screen and we can go ahead.
Okay.
Okay, that's great. Yes, that's great.
Yes, so I'm really happy to give the talk. I also gave the talk earlier today at the Royal Holloway University of London. So happy to give the talk again here in the nice Cardamom project. And I thought for you guys, it's interesting the low resource scenario. So in my search, I focus a lot on vector spaces, dense vector spaces, and also on neural search. So neural search, you input some query and you want to find the relevant hits, which can be images, other documents, and you use some neural network for this. If you have any questions in between, feel free to ask. I cannot see the chat, so if there's some question in the chat, maybe someone can interrupt me and ask.
I'll keep an eye on it.
Great, thanks. So in the first part, so the talk is in two parts. The first part is like a rant, or more critical thing, what is low resource and is low resource really realistic? And the second part is on some techniques about low resource, or which we currently try to do, but this is ongoing research, which we have not yet finished. So when you read current papers, the current hype, what you often see in many papers is like few-shot learning, or others say, okay, we get state-of-the-art results just using 20 examples. Some even say, okay, we do zero-shot learning, or there's a paper saying, okay, we get state-of-the-art embeddings with just 20 seconds of training, which sounds really amazing. The question is always, what you should always ask in the beginning is like, be critical about any field. Like, is low resource training actually possible? What can be what are the limitations when you're low resource? So can we really learn good models when you have just a few hundred examples? And I would argue that if you want a generic, widely applicable model, this is sadly not possible to just learn it from few hundred examples or from small data sets. Let me give you an example. So let's say you have the task where you want to match images and text, and you have the question where user asks the question, which image shows the Eiffel Tower? This is pretty much quite simple for most of you. So I hope all people here in the room were able to identify that image A shows the Eiffel Tower. So that's quite easy for us. Now a bit more complex example, which image shows the oak tree in Dötling? That's a small village, 1,000 inhabitants. I grew up in Germany. So everyone in my hometown knows how the tree looks like. It's really prominent in our small village. But if I show you here 4 different images, it's likely quite hard for you to guess which one it is. So maybe someone wants to give it a shot. So which of the 4 oak trees is the oak tree in Dötling?
I say A.
Got some A's and B's.
Some A's and B's and D's and B's and B's
B
and A. Yeah, so looks pretty much 25% chance. As mentioned, everyone in my hometown and everyone who has been to the town would know it's the image B. So you know it. If you have been there, you know it. If you have never been there, you don't know it. And what we have is like a long tail in relationship of objects of things. So if you can plot it. So if you take the number of people knowing the relationship of 2 objects, and you have the 2 objects, cat versus dog, Pretty much everyone knows it and can describe what are like common things between these two words, what are dissimilarities between cats and dogs. And then when you go down in the tail, the number of people knowing it gets fewer and fewer. So if you ask what's similarity and dissimilarities of C and Java, fewer people know this. Even less people know relationship of PyTorch and TensorFlow, and fewer people know Roberta versus dBERTer, and even less people, I would assume, know what's the difference between TSDE versus Mirrorbird. So you have an extremely long tail. Some things are known by billions of people, but other things are known by really few people. Some things are just known by 2 people, like maybe you and your significant other. Maybe you have some specific names for certain items, objects, and maybe sometimes are just known by yourself. And you have to see an example at least once. So if you have never seen the oak tree in Dirtling, there's no chance to identify it among other oak trees. If you have seen it, it's easy to identify it out of 1,000 images of oak trees. And if you think about how diverse and complex our world is, if you think about how many distinct animals, trees, flower, leaves, fish, monument, buildings, statues, national monuments, food, people, items, clothes, movies, drawings, art there is, and everything has a name and it is a concept. From there, it will be really hard to represent the complexity of the world with just, for example, 100 examples. So if you're interested in a foundation model, in a model which you can use for a lot of different applications, a massive data set is needed. So even when you have the most efficient training procedure possible, and it's sufficient to just see an item, an object once, you still need a really large data set. So if you have never seen the Mona Lisa, the drawing of the Mona Lisa, you cannot identify the image of the Mona Lisa. Also, what you should be careful is your benchmarks. So what we often see is that the benchmark is just testing the shorthand, like what's common. But what's really interesting in the benchmark is the long tail. So here are all the interesting applications. So you do not need a Google search engine if you want to find the URL for Facebook. But you need Google search engine when you have a complex programming question about PyTorch and how to compute the gradient. Then the search engine provides the value and provides you, all the benefit you have from the search engine. So the value is in the long tail, but our benchmarks are in the shorthand usually. And what we see is that systems behave quite differently on the shorthand and on the long tail. So sometimes you have system like system B, which has like a really quite consistent performance on the long tail. So throughout the data, when it gets less and less popular, it performs quite well. And then you have some systems which perform really well on the shorthand, but then you have a steep performance drop on the long tail. And in academia and science, we optimize for benchmarks. So we have some common benchmark like the blue benchmark, and we optimize and we want to get better on the benchmark, because when we're better on the benchmark, we can write a paper and publish the paper and say how amazing is our paper. So sadly, this leads that we optimize for system A, like a system this is really well, performs really well on the shorthand, but which might be horrible on the long tail. While for any application, you would prefer some system like system B, which performs well throughout this tail. So many commonly accepted benchmarks are extremely bad. So one benchmark in sentence embedding models is the STS datasets, which was also used in the original Espert paper, but it's extremely bad data set, which we'll also talk later about it, which should not be used because it's just testing the shorthand. And why are there so many benchmarks on the shorthand? First, it's easier to get data for it. It's easier to annotate. Annotation is expensive, and academics and also industry do not have so much money. So They often fall back to sheep student helpers or to crowd annotators. And it's easier to annotate there. So for example, let's say you build a data set on questions about COVID-19 and you want to find scientific papers on COVID-19. And then there are two queries. One is from the shorthand, like COVID-19 symptoms. You can ask a student from computer science or from linguistics. Here we have the COVID-19 symptoms. Here we have the scientific paper. Does it talk about COVID-19 symptoms? That's quite reliable and easy to do. But if I provide the same computer science or linguistic students the question impact of the PCV2 specific lymphocytes on the CD3 plus positive T cells, I would assume that 99% of your annotators would be totally lost and would not be able to annotate which scientific publications are relevant for the second query. Like a query an actual person in biology would ask and would need help to find correct publications on this. So annotating the long tail is really difficult, as you need experts in the respective fields, and experts in the respective fields are quite expensive. But we need these long tail benchmarks. The performance difference in the long tail can be quite different. So some systems perform well, others don't perform that well. And as mentioned, the value for applications and also users is in the long tail to get a good performance along the line. And also benchmark needs to evolve. So in science, we often stick to the same benchmark. We introduce some benchmarks and then we use it for 20 years because then it's easy to showcase the progress we make. But it does not make sense if the benchmark is not good, if the benchmark is just checking the shorthand. So as our models get better and as our training sets get better and better, also the benchmarks needs to get better, more challenging and more realistic. The challenge of long-tail benchmark is the explosion of number of topics. So we have some common English, everyone or basically everyone knows, like cat, dog, table, chair. So this is common knowledge shared by every adult. And then we have like different topics. So we have sports, we have technology, we have politics, we have fashions. And then in every topic, we have subtopics from technology. We have gaming, phones, AI, crypto, IoT. And then in AI, we have further even more subtopics, NLP, computer vision, and then even further subtopics. So we have an exponential growth of topics in the long tail. And you require expertise for every topic. So maybe your system works extremely well for AI, for questions in AI and finding scientific papers about questions on AI. But it could be that the system totally fails on fashion questions or on sports questions or questions from politics or questions from biology or geography. So you require experts for a lot of different fields to annotate these. And it's always a good question, like how many topics is your benchmark actually checking? Is it like a benchmark which just checks one topic, one narrow topic, or is it actually a benchmark which checks a lot of different topics? And are the topics really specific topics with a lot of domain expertise, or are they more from common English? Finally, in science, what we like to do is to work on the methods. So we spend a lot of time, we fix the training set, we fix the benchmark, and then we spend a lot of time, a lot of thinking, a lot of iterations to improve the performance. And here's an example on semantic search using MS Marco. So MS Marco is a data set from Microsoft using the Bing search engine, where they provide 500,000 annotated pairs of user queries and relevant documents. And if you train it with a really simple method, you get quite nice performance. And then there were like several iterations improving the method, and the currently best system is the test B system, or the best training procedure, where you get like a 2-point improvement in domain on MS Marco and like a 5-point improvement out of domain. In July, we took a bit different turns. So we had a community event at Hugging Face where we gathered a lot of different people interested in the field. And instead of trying to improve the training procedure, we started to collect more data. So we collected a data set of size of 200 million pairs of question answer pairs. So this is significantly larger than the previous train set. We used extremely simple training method. So it's the basic of the basic of the basic training method. And we train on this large data set. And we got quite a nice improvement compared to the previous approach, like some improvement in domain, but a 10-point improvement out of domain. And this took just 5 days of work. So if you compare it to like how much Sebastian spent on this introducing, tuning, and developing the test B system, compared to just 5 days of work downloading data sets, bringing them to a custom format, there's like quite trade-off in the effort to invest. So the summary of the first part, and I'm also happy for a discussion at the end on this maybe provocative statement. True low resource learning is not realistic, at least when you want to have like a generic model which you can apply for a lot of different areas and fields and tasks. The world has just too many facets. It's too diverse, too complex, too many aspects we have. And you have to see something at least once. You have to see the Mona Lisa at least once to know how it looks like. But there are some important research questions. How can you learn unsupervised? Like, how can you avoid the overhead that we have to ask users to annotate data? How can you exploit structure in your data? So if you have certain structure in the and in your data, like when you have websites, you have title and body. When you have a Wikipedia article about Mona Lisa, you have some text and you have the image. And also an important question is data efficiency. How can we learn a concept from a single instance? So how can I present my model a single image of Mona Lisa, and then it knows this is the Mona Lisa, and it can distinguish the drawing out of millions of drawings and say, okay, these are all images of Mona Lisa. We also need better benchmarks. They must evolve with the train set and when the models get better. And they should check the long tail. So please stop using the same benchmark for 10 years or even 5 years. I would say after like 1, 2, or 3 years, a benchmark is quite outdated and you need a better benchmark to actually measure progress in your field. And finally, we need more and better data sets. So improving data sets, improve models often more than tuning the architecture. So my advice when you work on low resource domains and languages, try to untap more data from your language, from your domain. Because we see a large imbalance. For English, it's really easy to get a lot of data. But for other languages, even high resource languages like Spanish, it's really hard to get good data sets and large data sets. And I could imagine if you go to less frequent languages or historical languages, it gets even worse. So yeah, please focus on the data.
Okay, we have a question that's actually quite a good follow-up from that, which is someone's asking, when can we say if a data set is of good quality? So what are the criteria for a good quality data set?
Yeah, good question. I think there's none, it's not answered. So I think it's really hard to say when is data good quality data in principle and when it's in bad quality. We humans are amazing to infer knowledge also from bad quality data. So even when we have noisy data, junk data, jokes, fictional stories, we're really able to read it, to understand it. Mm-hmm. So in principle, I would say in theory, bad data is just mainly random data, which is disconnected from anything. So when you create like a random number generator, this is bad data. But from everything else, humans are able to learn. but machines are not there yet. So for machines, they suffer from bad data. So if you have some noise in your data, some repetitions in the data, this hurts a lot the models. And this is in question, okay, how can we make our system so robust that noise does not matter to the system, and then they will just ignore the noise like we humans do. Okay, now there are 10 pages of noise, irrelevant noise. I just skip over them and go and find the next interesting part. But yeah, big open question and big, really interesting research direction, how to measure data quality and how to improve data quality.
Perhaps one thing that's very reliable is to you know, if a data set's been used in lots of papers, you know, lots of people have validated it and found that it works. So it tends to be a good quality data set if it's been used in lots of papers, but that also kind of works against your point as well, right?
Yeah, so especially when you do testing on it, you see that systems get more and more like this, that they overfit on the small part what the benchmark is testing, and they suffer extremely on everything else. So I would be really careful on the data sets, especially when it's commonly used, when hundreds of papers exist on this data set. I would call that people overfit on this data set and see to progress to the next data set and find the next benchmark which works better.
Yeah. There's a couple of interesting comments come in the chat. So Teresa's talking about it being dependent on context. You know, good data is something that works for a specific task and there's no general answer to it.
Sorry, can you repeat again?
So Teresa was saying that it depends on the context. You know, good data is one that predicts, you know, accurately for a particular task.
Yeah.
But there's no general answer.
Yeah. Yeah.
Yeah, and Emma is also saying that it depends on relevance.
Yeah.
You know, models are fine, but you have to have, you know, the problem is something akin to bad feature engineering on earlier tasks. You know, you have to have, the data has to be relevant to the task.
Yeah, I mean, we see that we go into more and more direction where we can work with noisier data and larger data sets. So we used to have like really clean data sets annotated by experts. Then we moved to crowd annotated data. And now we have like a lot of unsupervised data, like in these transformer networks where you take text from the internet and you do an autocomplete or masked language modeling. And it works well on large data sets collections. So if you train it on billions of tokens, it performs well.
Yeah.
And I think that's the research direction to go, like, how can we make the system so robust that it can learn even when you feed a lot of noise data in it? Because humans, I mean, you do not forget how the Mona Lisa looks like or how the Eiffel Tower looks like. If I present a lot of noise, garbage data to you, you still remember these facts and you just ignore what's noise.
Okay, thanks.
Great. Yeah, great questions. Yeah, the second part is a bit more technical. I want to start with some overview of neural search, like how do these systems work, what are current architectures, and then I want to present some techniques we're using to do domain adaptation. So how can you adapt these systems to new domains where you do not have labeled data? So the most simple architecture for search is using dense vector spaces. That's also like the SBIRD, sentence BERT, or sentence transformer architecture. You take some query, you pass it through a transformer network like BERT, you do some pooling. So for example, you do a mean pooling to get some fixed vector. And you do the same with the document, you pass it through the network, you do some pooling to get some fixed vector. And then you have the vectors in the vector space, and you can measure the similarity between the query and documents. And the idea is you map your query into the vector space, and then you check all the documents which are close by in the vector space. And you hope that these documents are relevant for the query. So that's a rough overview of bioencoder, also dense retrieval. Idea is to map query and document independently to vectors and then do operations in the vector space. Different architecture is neural re-rankers. It works in two stages. So you have some search query and you have some document collection, and then you have a first stage retrieval which can be any retrieval, any search system you want to use. It can be from the previous slide, the dense retrieval, where you have the vector space, but you can also use standard lexical search, where you search your document collections for all the documents which contain the words from your query. And then you retrieve, for example, 100 documents from the first stage. And then you have a cross-encoder re-ranker. So it looks at the 100 documents and looks at the query, and then it creates a ranked list at the end with the most relevant documents at the beginning, and then sorts them to the least relevant document. And you do this by a cross-encoder where you input the query and the document as one input, as one long string into a transformer network like BERT. BERT then does cross-attention between all the query tokens and all the document tokens. And at the end, it outputs a score between 0 and 1, how relevant is the document for the query. And you do this for all the 100 documents you have retrieved from the first stage retrieval. And then this gives you the list, the ranked list from the most relevant to the least relevant hits. Another approach for neural search is doc2query. It works with an encoder-decoder system here in red. And you input some document you have, like researchers are finding that cinnamon reduces blood sugar, and it outputs some questions or queries people could ask about this document. So the idea is here you produce queries, questions people could ask, and if they get this document as an answer, they would be happy to get it as an answer. So here you produce a lot of different, like 40 different queries, questions people might ask about this document. And then you do simple concatenation. So you have your document text, and then you add concatenate, like really string concatenation, your 40 different queries, and you index it in a lexical search engine like Elasticsearch. And then when the user query comes, so the user inputs some search query, some question, you do lexical search over the original document and over the generated queries, and you return the hits. And the encoder-decoder architecture brings two benefits. First, it generates some synonyms. So it sees the text, I don't know, maybe it reads New York City and produces a synonym like NYC, or sees United States and produces a synonym US. So it produces synonyms, so it expands the document with the synonyms you find in the document. And also it identifies which words are important in the document. And you find a lot of these words like cinnamon, blood sugar, in the generated queries. And then from your lexical search, where you do TF-IDF, so you do term frequency, you see cinnamon and lower blood sugar has high term frequency. So this has a higher importance and gets ranked higher in the hits. Another architecture is Colbert. So in the dense retrieval, you had one embedding for the query and you had one embedding for the document. And here in Colbert, you do a many-to-many comparison. So for the query, you get for every token in the query one embedding, and also for every token in the document, you get one embedding. And then you compare one embedding or every token embedding with all the token embeddings from the document. So that's a many-to-many comparison. So you take the first embedding from the query and you compare it to all the embeddings in the document, and then you take the second embedding from the query and compare to all the embedding from the document, and you always take the max score, and then at the end you sum over the max values to get a final score, how relevant is the document for the query. And there are many more architectures how people come up with neural search, how to use transformers to index documents better, to retrieve documents better, to rank documents better. And like every month, another architecture is popping up. So, but I think these are the most important architectures to know. And we asked the question, how good is neural retrieval? So you see a lot of this work has been trained on large data sets and then evaluated in domain. The data sets, they are often quite large. So they have often like 100,000, 500,000 of training pairs manually annotated. And this is only suitable for big companies, or if you have like a popular product. If you run the Google search engine, it's quite easy to get such large data sets. But for new companies, academics, or when you have some niche use cases, you're left out. Like annotating such large data sets is like really expensive and really hard to do. So we wanted to know in the first step, how well do models generalize to new domains and tasks? So can I take a model which have been trained on these large data sets and apply it to a different domain or to a different retrieval task? And the second step, also can research how can we improve the performance from unlabeled data. So I maybe have a lot of documents from my domain, but I do not have labeled data. How can I incorporate this knowledge to improve the search performance? And to test this, we created a new benchmark, the beer benchmark, where we collected a lot of different text retrieval tasks from really different domains, really different tasks. So for example, we have tweet retrieval, where your input is a complete news article, and you want to find tweets talking about this news article. From biomedical, where you have some biomedical queries and you want to find publications from this field. From scientific domain, where you have some scientific claims and you want to find papers validating or rejecting this claim, to some computer science questions, financial questions, and so on. So 18 different data sets on different tasks, what you want to do, what you want to achieve. Sometimes the queries are long, sometimes they are short, sometimes the documents are long, sometimes they are short. So really diverse benchmark. And then we tested a lot of different systems, how well they perform. So we compared them to the baseline BM25. BM25 is a lexical search system, which is really popular. It's implemented in all the big search products like Elasticsearch, OpenSearch, Lucene, Solr, and they are all based on BM25. And it does lexical search. And then we checked how often is a system better than BM25. And we see that BM25 plus a cross-encoder re-ranker is better on 16 data sets. So on 16 data sets, we see an improvement. And on 2 data sets, we see that the performance is actually worse. And the second best system was doc2query using a T5 system, doc-T5 query. And then on Colbert, we already see that it was better only on 50% of the data set, and on 50% of the data set it was worse. And then the TASB model is an embedding model. We see it was only better on 8 data sets, and on 10 data sets it was worse than simple lexical search. And then here at the bottom, for example, dense passage retrieval from Facebook, it was only better on 1 data set. On the 1 data set it was trained on, and was worse on 17 data sets. So lexical search remains a strong baseline. So it's hard to beat if you do not have training data. And BM25 plus a cross-encoder re-ranker performs the best. And embedding models, they have issues with unknown domains. In general, benchmarking is difficult. So in benchmarking, information retrieval benchmarking, only a tiny fraction of query document pairs is annotated. If you have a collection of 10 million documents, you're not able to find all the relevant documents for the query and to annotate them. So what you do is you have only a small set annotated, and you assume that all the other documents or the other 10 million documents you have are irrelevant. And how to get these documents to annotate? You use some existing systems, some existing search system, which are predominantly lexical models. You retrieve with them, for example, the top 100 most relevant documents. And then you ask your annotators to annotate these 100 documents. And we were asking, like, how many unannotated documents are other systems retrieving? And we measured this using the hole at 10 rate. So the hole at 10 rate is the number of hits a system is retrieving in the top 10 position, which has not been seen by an annotator and which is assumed to be irrelevant. So for lexical search using BM25, we see that 6% of the hits have not been seen by any annotator and are assumed to be irrelevant. If you use BM25 plus a cross-encoder, just 1.6%. So most of, or all the hits have been seen by some human and judged as relevancy. And then if you look at newer approaches, which are not based on lexical approaches, like DPR, NC, and TESB, which are based on embedding models, you see that up to 30%, like 1/3 of the hits they're retrieving, have not been seen by an annotator and are just automatically assumed to be irrelevant. We then did a manual annotation of these missing pairs where we do not know are they really relevant or not. And we saw that it changed conclusions. So if you take the original track COVID-19 dataset, which is like really recent benchmark and really popular benchmark, we see, for example, that the ANSI model is weaker than the BM25 baseline. So you would say, okay, ANSI model, it's a bad model. It's worse than BM25. However, when you add the missing annotations, we see that the ANSI model is a lot better than BM25. So here the conclusion is benchmarking and information retrieval is extremely difficult. And also your benchmark has to evolve. So when new types of architectures, new types of retrieval systems, like these embedding-based retrieval systems pop up, and you have to include this in the benchmark to provide a fair benchmark to new systems and to show, okay, which systems are actually good and which systems are not so good. Also, there's sadly no free lunch. So I said that BM25 plus a new re-ranker works the best. It's generalized nicely. It also gives like nice performance gains, but the downside, it's really slow. So here you have the latency. If you input a search query, you have to wait half a second to get your results. And in search, you do not want to wait. You want to have your results instantaneously. Especially when you run it on a CPU, you have to wait 6 seconds before you get the results. Just imagine you would input something into Google and you have to wait 6 seconds to get the results. Similar for Colbert, it also works nice, generalized nicely, but it's slow and has quite a large overhead in the index. So you need machines with a lot of CPU memory, which gets really expensive. And doc-T5 query is nice at the inference, but it's extremely slow in indexing. So generating these queries for passage is extremely slow. And if you have to index a large data set of millions of documents, it's really slow and really expensive to do so. Single vector models like dense embedding models, they are efficient. They are like fast. So the retrieval is quite fast and the index size is also manageable. But they have issues with out-of-domain data. So there the problem is with new words. So some new words appear, like some new company name, some new band, some new movie, and it has to put the word somewhere in the vector space, but it has never seen this word in the, and does not know what's the relationship. Is this word a company? Is this word a movie? Is this word an actor, a musician? So where should I put it in the vector space? And so the big question for these models, how to perform domain adaptation without having labeled data. So if you go to a different domain, you have a lot of these new words of these new terminology the model has not seen during the training time. And how can you do this adaptation without requiring that you ask humans, okay, please annotate 100,000 data pairs? One of the most simple procedure is masked language modeling, which was done in the original BERT paper. So you take a word, you replace it by a mask, and ask the model to predict the word. A different approach is from this year, it's MirrorBERT, and in concurrent work called SimCSE, where you take sentence pairs and where you apply a dropout. And if you apply dropout to the first sentence and to the same sentence in the second time, the dropout is slightly different, leading to a slightly different embedding. and you want to have the embedding for these two sentences close in the vector space, while you want to have this embedding for sentence 1 and sentence 2 to be as far away in the vector space as possible. Also proposed this year is CT. It's similar to SimCSE, but instead of using the same model with dropout, you use two different models. And when they see the same sentence, it should be close in the vector space. If they see different sentences, the two models, they should be far away in the vector space. And one work by my PhD student, TSDE, it's transformer-based denoising autoencoder. The idea is on a denoising autoencoder. So you take some text with noise. So you take the text, you delete randomly some tokens, you pass it through a BERT encoder, and you get you have some pooling to create a fixed sized embedding. So here you have a 768 dimensional embedding. And then from this fixed sized embedding, you have a decoder, which creates the text without noise. So it's standard denoising autoencoder. You have a text with noise, and you want to have the text without noise. And in the middle, you have the restriction by mapping all the input knowledge or the input text to a fixed size embedding. So far, unsupervised methods have been evaluated on STS data, but this is an extremely bad way to evaluate, especially unsupervised method on. Because first, what we see is that the performance has near zero correlation to performance on real-world tasks. So if you want to use the system to find similar publications about COVID-19, you don't see any correlation how well does it perform on STS versus how well does it perform on COVID-19 scientific publications. And the issue is that the STS data set has a lot of simple sentences like a dog is playing in the park, a man is cooking spaghetti, a woman plays a guitar, and they don't require any domain-specific knowledge. So you don't need any knowledge from technology, from biology, from math, from fashion, from sports to understand these sentences. So the test is extremely on the short head, but you want to use the systems usually on the long tail. Also, by the setup of the data set, it has an unrealistic label distribution. So the authors of the benchmark, they sampled pairs with roughly equal label distribution. But what you see is that only few pairs are really relevant. So you have one specific question and only few hits are really relevant for your question. And all the other, like 99.99%, are irrelevant. So this is like a realistic distribution, which is not represented in the STS data set. So in the TSDE paper, we propose a different evaluation based on 4 specialized domains. One is about questions on Ubuntu, then one on different Stack exchanges, one on Twitter, and one on scientific publications. And what we see, the difference in performance. So what we see that MLM, like the oldest method we tested from the original BERT, is actually better than systems proposed this year, like CT and SimCSE. And also CT and SimCSE, they're weaker than out-of-the-box models. So it does not really make sense to take them and to spend the effort to train them if you can just download the model and use them. And TSD was able to slightly outperform the out-of-the-box model. However, the improvement is not so large. So if we compare to individual data sets, so here we have the unsupervised performance compared to the out-of-the-box model. So we see on Ask Ubuntu, it's weaker, performs weaker than the out-of-the-box model. On Twitter paraphrases, it's weaker than the out-of-the-box model. On Stack Exchange, it's weaker. So only on the scientific publications it was able to outperform the out-of-the-box models. So it's really hard to beat the supervised pre-trains, the supervised models, the supervised out-of-the-box models. And the diversity of the data set is quite critical. So if you have a large data set, you get good results across the task. That was also the reason why I focused in July to create a really large data set of 1 billion pairs. So we collected 1 billion pairs of sentences which are in a relationship, which we consider as related, and train on this large data set of 1 billion pairs. And this model shows like really good performance across many areas because it has seen so many topics, also topics from the long tail, from fashion, from crypto, from Internet of Things, from sports, politics, economy, and so on. So having more data is beating again, having a better training approach. However, what's interesting about these approaches is to use them for pre-training. So we took them, trained them on a large corpus, and then we trained them with some labeled data. So here we see the number of labeled pairs. And here in blue, it's a bit hidden. We see the baseline if you just go take directly BERT and train it. And then in green, we see when you do mass language modeling. And then in orange, we see the performance with the denoising autoencoder. And we see quite a performance gain even when you have fewer data. So even when you have 1,000 training pairs and you do the pre-training with TSDE, you get quite a good performance compared to just taking directly BERT and train it on your domain. We also tested for the case where you do not have any labeled data. So maybe for your domain, you just have unlabeled data, but you don't have any labeled data. But for other domains and other tasks, we have a lot of labeled data. Like as mentioned, we have like over 1 billion, 2 billion pairs for English, labeled data for English. So we trained the TSDE on the unlabeled data. So this just requires that you have text from your domain. And then we did standard fine-tuning, supervised fine-tuning on the existing supervised data. And this is the domain adapted model. And we tested it in two ways, first doing supervised and then unsupervised. This does not work. But if you do it in the opposite direction, first do unsupervised pre-training and then do supervised training on the data you have, you get some improvement over the previous purely unsupervised system. We also currently do it for semantic search. So semantic search, you have a short query given and you want to find relevant documents for that. And if you do not do pre-training, you get a performance on 6 different tasks and domains of 44. And by doing the pre-training and then doing supervised training on existing data, you get a 4.7 improvement, which is also quite nice. Here's a teaser for some upcoming work from a PhD student, GPL. It's using the idea from doc to query. So you have your passage given, you have your T5 system that produces questions people could ask about this paragraph. And you use this to create a data set to train your embedding model on it. And you generate a lot of queries for all the documents in your domain, and then you tune your bi-encoder on this. And this improves the search performance by 4 to 10 points, which is quite a big improvement for NDCG at 10. So it's not marginal improvement, but you as a user will actually see and feel the difference if you take the model out of the box, where you get like 44 NDCG at 10, or if you take a domain adapted model where you get like 50 up to 51 NDCG at 10. So this is a really nice way how you can adapt a model to your domain without having labeled data in your domain. So the summary on the second part, unsupervised sentence embeddings do not work that well yet. They have worse performance than out-of-the-box models, which were trained on diverse data. And they also quickly converge. The authors of MIRBIRD put it as a big advantage. So in the abstract, they advertised the method. It's so great because it's trained within 20 seconds. But this actually means that it does not matter if you have 1,000 sentences or 1 billion sentences from your domain. So after 20 seconds, the model will not learn anything further. And overall, this means it does not learn anything about your specific domain. So if you apply it, it does not learn about your specific domain. So if you have COVID-19 scientific papers and you want to apply your system on that where you don't have labeled data, it sadly does not learn anything specific about this domain. Domain adaptation, what works is to first do unsupervised training and then to do supervised training on the data sets you have. And there, the current best system is the TSDE system, followed by ICT and masked language modeling. It's unclear how to adapt an existing model to new domains. So it would be nicer to first do one time the supervised training and then somehow be able to unsupervised transfer it to domains. But so far we were unsuccessful to do it in the computational nicer way where you do supervised training only once and then do unsupervised adaptation. And query generation with GPL is promising. We see quite strong improvements for domain adaptation using this approach. And as mentioned, it's upcoming work, which we hope to publish next month. Conclusion, work on your data. We need better data sets. So even such, there are a lot of data sets and large data sets. We still need better data sets, especially for languages other than English. Also, don't forget about the benchmarks. Many papers overfit with a narrow evaluation on the short head. So they just tested on one data set, on one benchmark, on one data set, on one task. But the conclusions they draw do not generalize if you go to a different task, if you don't go to a different training set. So there's a lot of work needs to be done in the benchmark. And in benchmark, we need better, more diverse long-tail evaluation to really evaluate how well do the models perform on complex tasks. Unsupervised learning is the future. So far, we have great results with supervised data, like query and relevant documents. But this is really hard to scale to many domains, to new languages, to low resource languages. So how can we learn the most from unsupervised learning? And so how can we learn the most from as little structure as possible? And I would say there are different hierarchies of structured data. So if you have annotated data, like you have some query and some relevant document annotated by a human, this is a lot of structure. And hence you have like little data from that. You can get more data when you try to mine the web. So there's a recent work from Facebook where they mined 130 million Q&A pairs from websites in a lot of different languages. It requires less structure, but you get more data. If you just require a website, the title and the body, or the text and the image in the website, that's even less structure and you get even more data. If you just require individual documents and can exploit the document structure, like that most documents tell a coherent story, you get even more data. And yeah, when you go further, like you just require individual paragraphs or individual sentences, you assume less and less structure and get more and more data. And so the question is like, how can we require as little structure as possible? And this enables us to get as much data for training as possible. So how can we, for example, train really good systems where we just use the website title and the website body, where it's easy to get billions of these billions of these pairs from Common Crawl for a lot of different languages you can find on the internet. Yes, that's the conclusion of my talk. Looking forward to your questions.
Okay, thanks a lot. Do we have some questions in the chat? All right, there's one already. It's very long. Rolando, do you want to maybe ask yourself or?
Let me see. Sure. Thank you. Let me just activate this. Hi, Nils. Hi, John. Hi, everyone. I hope you're doing well. Let me read it myself. So, Nils, thank you so much for your talk. I wanted to ask about like seriously smaller data sets, like 10,000 sentences and stuff like that. And that's all there will be. So I in particular work with a language from Central America. We got 10,000 sentences out of everything we could, a dictionary, grammar book, a couple of children's books that there are, but to get anything more, we'd have to synthetically generate it. So that's pretty much what there is.
Yeah.
And we're obviously a long way from having large data sets. We have tried to make word to vex. We haven't tried to vectorize the sentences yet. We faced the benchmarking problem because obviously it learned easy things like the relationship, like cat and dog are closer than cat and tree. Yeah. It was worse when you have culture-specific relationships. So they have special words for brother, like brother of a man and sister of a man and so forth. It learned it, but less so. And it was terrible with grammatical relationships that were specific to the language, like learning relationships between like one human, like one of human is similar to one of animal, for example. It was really bad at it. So I can see how there is a relationship between like these results and the semantic relatedness that you drew, that it's doing worse when it has to learn more specific things. So as for question answering, we would have to probably build the questions manually, not just because we can generate them ourselves. We're barely making the dependency parsing of the language, but we would have to make them along the spectrum that you showed, where there are very easy answers here, but very culture-specific ones at the bottom.
Yeah.
Which of the architectures that you have here would you recommend for working on such a low resource problem?
Yeah. It's a really interesting problem. I mean, for a lot of languages, you don't have these large data sets. So I don't know, even when you get everything on the internet, in books, in libraries, you still end up with like small data sets. First, I think the expectation has to be a bit different. I think you cannot assume that such a model on this language will be able to tell the difference between PyTorch and TensorFlow. So I think you cannot expect that it knows, or you have text on PyTorch and TensorFlow and Roberta and Deberter. So you can just test, but can just get a model which works well here. I think what makes sense is to pair it with like some high resource, language. So if you go as a human and you learn a second language, let's say you learn German, you do not learn every concept new in German. So you don't learn what is German cat and what's the German dog and how is it connected. But what you learn when you're like, say, native English speaker, you learn, okay, in German, the cat is eine Katze and the dog is ein Hund. And then you can transfer it back to your native language and you know, okay, what are the similarities and dissimilarities of these two concepts. So basically what you do as a learner of a second language, you take the other language and you map it back to the original language. That's what I would also recommend for these low resource languages, that you try to find, so what I find interesting is there any language which is linguistically similar? So maybe, I don't know, Spanish is similar. And you could
just think, we do have a parallel corpus with Spanish, so we can look for things like cat and dog. The really interesting things like the family relationships and stuff are the ones that are going to be flattened out in Spanish. And unfortunately, there are a couple of similar languages, but this is by far the one we have worked in the most. So we don't have a comparable corpus for the other one.
So I think it makes sense to find either like linguistically similar languages and then try to do the mapping. So you go from your low resource language and map it to Spanish, or you can also do it to high resource languages, so to English. So for English, you have the most data, and you just try to map the concepts from your low resource language back to English. So you know, okay, this is a cat, this is a dog, this is a table, this is a chair, this is the color green, this is hot, this is small, this is loud. And then to be able to learn it or infer it from English. But of course, what you miss are these cultural specific, historic specific, which is just in this one language, which is just there in this one culture. But I mean, it's the same. If you come to Germany, you can learn German from books, but some German specificities of our culture, you will not get it. and you have to experience it by interacting with Germans living in Germany. So I think you can get it to a certain degree to work well on these common things, but to work on these cultural specific things, I would say you need more data, like somehow find more data, and research work on to be more data efficient. Like humans are extremely data efficient. You see, as a human, you see something once. So I tell you, Joe Biden is the new US president. You immediately update your knowledge that Donald Trump is the previous US president. The first lady also changed, is now also Biden, Jill Biden. But our models, they're really bad in terms of data efficiency. So if you take a BERT model, BERT thinks that Barack Obama is the current US president, and you have to throw a lot of text at BERT to update the knowledge in BERT that Obama is no longer the president. So interesting research line, I would say, is how to make it more data efficient. How can it learn, in the best case, from a single example? But it's a long way to go there. So.
And which of the models that you showed today would you recommend for a first experiment in question answering in such a low resource language?
Yeah. So what works best is this approach with the re-ranker approach. You have some first stage retrieval on lexical, and some standard lexical retrieval where you input the query and you find the documents which have the terms. And then you have a cross-encoder re-ranker, which looks at the query, which looks at the document. Here, the nice thing is that it can do a word-to-word comparison. So it can look at the words and see are there matching words in these two pairs. Approach like this requires a lot of training data because you have to find like a good vector space. You have to know, where should I put a cat? Where should I put a dog into the vector space? And should it be close in the vector space? At which angle should it be in the vector space? So at such an approach, you need a lot of training data, like 100,000 of pairs. But here with such an approach where you do a pairwise comparison of the query and the document, at least for English, you find that it works well when you have little data. The question is like, can you train a BERT transformer network like pre-training when you have like low resource domains? But I mean, they're the multilingual research direction where they train models on a lot of different languages and also generalize nicely to other languages. Lower resource languages are quite promising. So I would take big multilingual model like XMR and train a system like this if you do want to do neural search in your low resource domain.
Thank you.
Okay, great. Do we have another question? Maybe I'll sort of add a bit of a comment. I mean, we've also been looking at unsupervised embedding. We actually have a paper at EMNLP in a couple of weeks, and we find that some of these effects actually do work where by training on lots of languages, we can actually use kind of related language phenomena and even unrelated language phenomena. So we do find that this actually unsupervised in the area of under-resourced languages does actually outperform supervised training, because you can project so much from other nearby languages. So that's something we're presenting in a couple of weeks' time. So we've got some good results for that.
Are you going in person to EMLP or do you do a remote presentation?
Afraid not. It'll be remote. I think it's still a bit. Our university still has some rules about traveling.
Yeah, it's still super complicated, sadly.
Yeah.
Yeah, I think there's a lot you can learn from other languages, like I don't know, from linguistically similar languages, but also concept-wise. Like, I mean, even when your language is not similar to English, you can learn a lot about, I don't know, Mona Lisa. How does the Mona Lisa look like? When was it painted? Who did it paint? And then you can infer it from the English model to your lower resource model.
Okay, great. Is there any other questions or? Okay, Well, so I mean, it was an amazing talk, really interesting. So thank you very much. Yeah, and well, we'll put the recording up on YouTube afterwards for anyone who couldn't make it. And yeah, and well, I'd just like to say thank you all for coming. We'll have our next seminar. I guess I can't remember the exact date off the top of my head, but it's a month. And we'll have William Lamb from Edinburgh coming to talk. More sort of a historical Irish, so moving again into the sort of the more linguistic side of talks. But otherwise, yeah, I just want to say thank you, Nils, for time. Really good talk, very interesting, and thank you everyone for coming.
Great, thank you. Bye-bye.